Okay, this is lesson D1 on oscillatory motion. And so first thing we're going to do is just a quick recall on the relationship between period and frequency. And essentially they are inverse relationships, right? Period is equal to 1 over frequency, or frequency is equal to 1 over the period, where big capital T stands for period. Okay, give this a quick little try. 12 waves come in at a time of 60 seconds. What's the period and frequency of the wave? Pause the video, give this a try. We'll see you in a moment. Welcome back. So you should have calculated that to be 5 seconds per wave for the period and a frequency of 0.2 hertz. We're going to just do a quick little recall. First of all, Hooke's law, as you will recall, we've done in the past. Force is equal to negative kx, where k is the spring constant, x is the displacement from the equilibrium, and all this negative is this direction, saying that that force, the restoring force, is in the opposite direction of the displacement. So if the spring is compressed to the east, it will force it to the west. And Newton's second law is F is equal to ma. And so as we start to take a look at oscillatory motion, what we're looking at is things moving in simple harmonic motion. Now, in this case here, we have an object moving in simple harmonic motion. At this point here, we've reached the amplitude. We've got the largest amount of acceleration, in this case in the down direction because it's been compressed up. And the object has come to a complete stop. So we have the maximum displacement, maximum acceleration, where the displacement and acceleration are in opposite directions, and the velocity has reached 0. And so it starts moving down, eventually reaching the point where it reaches its equilibrium. At its equilibrium, it's moving the fastest, but no displacement and no acceleration now acting on the object. Moving back down to its opposite position, where it reaches its amplitude again. Maximum acceleration, this time it's accelerating upwards because it has its maximum displacement downwards and has stopped moving. And so we can see that motion continue on through the complete cycle. Okay, so we will see that you will have maximum velocity at the equilibrium. Maximum displacement and acceleration at the amplitudes. Right? And so where you see the maximum acceleration, so at the amplitude, you're going to see minimum velocity at the amplitude. And you're going to see a minimum displacement and acceleration at the equilibrium. Okay, so let's take a look at a couple of examples of questions we might face dealing with this stuff. First one, how far will a 250 gram mass stretch a spring with that spring constant? Well, we're looking at force is equal to negative kx, or that force is caused by gravity is equal to negative kx. And so in this case here, mass being 0.325, g being negative 9.81, all divided by k, which is 37.5. We'll get you the x, or x is equal to 0.0850 meters, or 8.5 centimeters. Will be the displacement. Second example here, we've got a 55 Newton per meter spring, compressed 0.15 meters or 15 centimeters. And how much could accelerate this ball? So we're starting in this squish position. It's going to accelerate the ball as it moves towards its equilibrium. And so here, again, F is equal to negative kx, and F is equal to ma. So we can actually equate these two. So negative kx is equal to ma. The spring constant we've been given is 55 newtons per meter. It is compressed 0.15 meters. We're going to divide that by the mass of 0.125 kilograms, which will get the acceleration. Now, the reason why we're changing kilograms is because we're using standard units, Newton being a kilogram meter per second squared. This is going to accelerate negative 66 66.6, but 66 meters per second squared. Now that negative again is just talking about the direction. So because this was compressed the way we drew it to the left, the acceleration was to the right. Now if it was compressed to the right, it would accelerate to the left. If it was compressed north, it would accelerate south. Always just in the opposite direction of the displacement. Okay, and taking a look at one more example here. Again, if this was oscillating every 0.3 seconds, what is the frequency? Well, we've been given the period, so frequency is just equal to 1 over 0.3 seconds, or you wind up with a 3.3 hertz as being your frequency. Okay, we've got a question for you to try here. Just give this one a quick try. 500 gram object accelerated by 75 Newton meter spring at its amplitude. And how fast is it going to be moving? Give this one a try, pause the video, and we'll be back soon. So in this case, force is equal to mass times acceleration, or kx, again, Hooke's law. And so we are going to equate these two, and we find the acceleration to be 9.75 meters per second squared. Now, yeah, I forgot the negative there, so we should put in that negative. It won't make too much of a difference here because the displacement and acceleration are actually in the same direction here. And so what you wind up with is using Vf squared is equal to Vi squared plus 2AD. Find that the final velocity is 1.13 meters per second. Okay, thanks for watching, and if you got any questions, let me know.